All right, welcome everyone to today's seminar. I hope everyone had a good long weekend last week for those who were in the US or Canada. Today, I'm happy to have Donglai Ma here to speak with us about Earth's radiation belts from a machine learning to a physical understanding. So Donglai is currently a PhD candidate at UCLA working with Professor Jacob Bortnick. He graduated from USTC with 2 bachelor degrees, one in space physics and the other in computer science. His major interest currently is in space physics, in particular wave-particle interactions, radiation belt modeling, and space weather. And I'm delighted to have him here today to talk about radiation belt modeling and machine learning. So with that, Donglai, if you'd like to take it away.
Thank you, Kyle, for inviting me. It's very exciting to present here. So I'll just start. If you guys got any question, I guess the process is tapping the chat. I'll answer at the end. So today's topic is Earth's radiation belts from machine learning to physical understanding. I would like to thank all the co-authors who support this work. This is not just the one work, but like combined with 3 or 4 different papers, which I major conveyed during my PhD career. So yeah, any questions is very welcome. And thank you all for listening. Let me go. So before I begin, I would like to talk a little bit about the AI explosion we are experiencing. I'm pretty sure everyone is hearing like GPT-3, GPT-4 recently and tried it. One thing is like I said to ChatGPT, like, could you come up with some line plots to demonstrate the AI explosion? AI explosions this year, and look, this is the result. And like if you ask it to show the code, it directly shows it. But it's not here to show like how good is GPT-4. It's to tell you like, okay, if you consider the number of parameters of those AI model as the power of those large language model, and this is like the log scale of the number of parameters. It enhanced by 10,000 times in recent 8 years. And what could we learn? I think for us, it's very important to adapt it and also to learn how to use new model ways, because they change their computation ways to like a GPU card, highly parallel algorithms. But like if we compare it with like all the data we got, all the code we got, it's not comparable. So right on the left, I'm showing the satellites we launched since there was satellites, and look at the comparison here. So we can now understanding like why like we are kind of a little bit slow comparing with the AI industry, because we don't have much power code, we don't have much data. So I think that's the future like we need to do. Okay, so that's a little bit about the AI explosion. The physics we are carrying, we are talking about today is radiation belt electron flux. So on the left, I'm showing the one probe MyGuess observation, and the right is the RBSP REPT observation. So the left is energy electron flux below 1 MeV, and the right is above 1 MeV to 7 MeV around. When we can directly see that it's including a lot of rich dynamics. It got a different time scale. Their response to the storm is very different. Sometimes it's enhancement, sometimes we can see the dropout. And we know like those high energetic particles can do damage to the satellites, and the low energy particles can provide source for wave particle interaction that can be enhanced to very high energy that we are interested in. So it's very important to model the electron flux across all the energy. The question is how to model it. And it's been a very popular topic in radiation belt physics. The traditional way is using Fokker-Planck diffusion model. So for a very simple 1D model, it's like a radial diffusion with source and loss. But if you really look at the 3D in phase space density, you need to include a lot of pitch angle scattering, energy change. So it's very difficult. And it's the most important part is it needs a lot of assumptions. For example, what's d alpha alpha, what's DLL, what's d alpha L? Those things usually parameterized by some, for example, like KP index. And another thing is those assumptions are like quasi-linear assumptions, which means it cannot capture the nonlinear dynamics. And it always needs the wave properties. You need to estimate the wave properties, the distribution of wave, and some artificial boundary conditions. Although it gives very good performance when you got good boundary conditions, for example, like the one I showed, which is the verb very good code, it's still like not applicable in space weather, or like I'm not going to say not applicable, but it's difficult, and you cannot assure that it captured the exact physics there, right? What we did is that we want to use a machine learning model to reproduce what satellites have seen. So the idea is we use history of those geometric indices. We always have good measurements on the Earth, and we reproduce the flux we can see. So for example, if we want to model the flux at some L shell at here, right, as I seen here, you can use the time history of those geometric indices, for example, AL, SMH, solar wind, speed of the solar wind, and the pressure of the solar wind to model the flux. The reason we can get this is that the good coverage of the Van Allen probes data, if you look at here, it's on the equatorial plane, and it got 2 satellites fly in and fly out. So it produce very good data set for us to model. And another important thing that being our motivation is that we know Van Allen probe is doing a very good job, but it turns down in 2019. What if, like, we cannot always have Van Allen probe, we cannot always have satellites there. So if not, how to produce those boundary conditions for Fokker-Planck diffusion, how to know what's happening, it's difficult. So if we can do this machine learning model that's only driven by geomagnetic indices and solar wind conditions, we can get the flux and we can reproduce what satellites have seen. So that's the big motivation we have. Now let's talk about how to train this model, which is very struggle thing when I first when I was in my first year of PhD student. So one thing is, if we want to model the electron flux only by the time history of geometric indices, one thing we really need to consider is the lifetime of electron flux. So on the left, I'm showing Seth Claude-Pierre in 2020's paper, which is the lifetime of the electron flux at different energy, color-coded by the color-coded here. So you could see that if we only consider higher L shell, which is more dynamic thing, and you could see that here, the lifetime in the inner lower L shell is very long. So we don't want to model that because it's very stable. For higher L shell, it's usually like 10 days. And the important thing is for higher energy, you could see that their time scale is higher. And for lower energy, it's like a lower time scale. The reason is that for higher energy, it means the dynamic scale of different energy electron flux is different. And for example, this is a very on the right, I'm showing a very early version of our electron flux model. So on the top is the observations, and on the bottom is the model result. Although you could see it's kind of capture the dynamics, one thing you could notice is that there is a very clear dropout there, which should not be there. The reason is that previously we thought, oh, the storm usually, like when you got a pressure, when you got an enhancement, it only drive the flux like by 2 days or 3 days. But the important thing is, if you use a very short dramatic indices as the driver, you could see that here, the red part is point to the driver we used in this machine learning model. It cannot capture the storm happened 10 days ago, like 20 days ago, which is like approximately this lifetime of the electron flux. So that if we don't only want, we are not only trying to capture the enhancement, for example, like here, we also need to capture the like duration of the electron flux. So this means we need a longer time history to capture the storm happens like 10 days or 20 days ago. So that's one important thing we met in this modeling process. Another thing very important but very simple is that when you train the model, I'm pretty sure everyone heard, like when you train the model, you need to use a training data set, you need to use a test data set, you need to use a validation data set. But when we dealing with the satellite measurement, how to do that? And it's a very important thing because usually when people do this, we just use random splitting. So for example, here, you can imagine each one is a data sample, but you split by the training and validation data set. But remember, the resolution of satellites is low. Even though you bind it to 5 minutes, comparing to the electron flux dynamics, the nearby data is always mirroring the same thing, which means when you split the train test data set randomly, it will cause the data leakage problem, which means is that you got the same data in the training data set and the test data set. Another thing is, okay, so if we cannot split it randomly, can we split them like yearly? So for example, we use 2000 data in 2014 as the test data set, and other 4 years is training data set. It's okay, but it's, how's that? We got some better ways, because if you look at the electron flux here, you could see clearly there is a bias in like 2014, the flux is much lower than other years. There is no much dynamics during this year, which means that this biased data distribution could give you different distribution data in training and test data set. And if we are familiar with machine learning model, we know that we need a similar distribution in both data sets, right? So the way we deal with this is we split the training and test the data samples by segments of like 2 days or to 30 days segments. So the choice of this segments is to ensure that each segment is much smaller than the total length of the data, which is 5 years, 6 years. And also it needs to much larger than the resolution of your input and target. For our input, we use element data set like 5 minutes. For the target, we use, for all the samples of the electron flux measurements, we use like 5 minutes resolution. So those 2 day and 30 days segments is much larger than the resolution of input target. And then we randomly split those segments in our training and test data set. So in this way, we can ensure that the data distribution in both training and test data set is similar, and also there is no data leakage problem. Okay, so here is our model performance. So on the left is the MyGuess 235 keV electron flux, which is like source and seed electron flux. And the C panel is the observation, and the D panel is the model along the trajectory. And the last panel is the model on the equatorial plane. So remember, we got the input of L shell, MLT, and M latitude. So we can reconstruct on the equatorial plane. So you could see it and another important thing is this is out of sample data. So that during the training, the data did not see those samples measured here. So you could see that the model captured the enhancement here, captured the slowly decay of the electron flux. And for another storm, it again captured the enhancement. For lower L shell dynamics is also captured. So it basically captured every dynamics we are interested in this energy channel. And this is like a shorter time scale, like a storm, not very strong, but like a medium storm. And for longer time, we can still capture it. So when we train the model, we use data after 2018 as an out of sample data set. So on the right, I'm showing another energy channel for like around 600 keV electron flux. You could see like during this 1 year time period, also out of sample data period, we can still capture all the enhancement, all the dropout, and even for this very intense storm, we can capture the enhancement and we can capture this penetration depth of the electron flux here. One thing I forgot to mention is those white period, because we don't have AL data at that time, we use a model AL data from Silberder from Professor Xin-Lin Li's model. So there are some gaps in the provided SolarWind data, so that we reproduce those white process. But other than that, the model performance is very good. And also another important thing when we write the paper is that when you look at your model performance, usually people just look at the R2 score, right? But the R2 score can cheat you, or the like a linear correlation coefficient of the measurement and the model, because your satellite is flying outside and like outward and inward the Earth. So it automatically produces some enhancement and the decrease of the electron flux, provide your variation, which means your R2 score for all the data samples will cheat you. It's not the real performance of your model. So the way we do that is that we fix one L shell, we check all the performance on all the different locations. It gives us very good performance. So you could see here, it captures all the enhancement there for the like single L shell, right? Another thing is, once we got the model, we not just trying to reproduce the data one probe has seen. When we want to model, for example, like we want to model the data out of those 2013 to 2019 period. So back in 2008, we can model this. So this is the SAMPAX data measured, like SAMPAX is an LEO orbit satellite measure the flux. So if we use our model to input those geometric indices, we could see that we can reproduce those flux very well in 2008. And this proves us that our model is deliverable for all the years, not just in those period in valence probes period. And also, once we got those very good performance model, we can do some real-time observation. So this is cooperation with Space Environment. We technology, this is a company. We put our model there, and we use some predicted geometric indices, for example, like DST and other geometric indices. We can reproduce the real-time electron flux that we observed, we should observe if we have one probes. So this is one observation. Another thing is I would like to show is this. So this is last month when I was in JAM meeting, Geospace Environment Modeling. right? It's a big seminar. I'm pretty sure everyone knows that. This is one observation showing by Professor Lee. In Seal Boulder, they got some how's that? In Seal Boulder, they got some CubeSats, and they shared their very first measurement of this electron flux. This is like a 1 MeV electron flux. You could see this is a very strong storm, minus 200. It captured this enhancement here. And this is our machine learning model. You could see some jig-jag there because what I used is a very poor ACE data measurement to use. We don't have Omni data set for this period right now. We just have uncalibrated solar wind data. But you could see it did a very good job. It captured the enhancement. It captured the flux level very similar, and also the move in, the penetration of the electron flux to lower L shell, right? So our model is very good to deliver, and yeah, it crossed all the energy from 50 TeV to 2 MeV, 3 MeV. It can capture those dynamics with only geometric indices input. So we think we did a very good job for that. And this is like the first part of the model part, that we did some machine learning model to reconstruct the electron flux. I think I would like to accept some questions because I'm ready to move into the next part. So Kyle, could you like ask some questions? Like,
yeah, Donglai, we don't currently have any questions at the moment,
okay.
So I think you're good to move on.
Okay, perfect. So yeah, so the question, well, we always have question, is that comparing with Fokker-Planck equation. Fokker-Planck equation tells you how the particles interact with wave in quasi-linear way. You got different waves. You can slightly change the particles in the phase space. So we know what's happening in the Fokker-Planck equation, but we don't know what's happening in the machine learning model, right? So you just input those geometric indices into the model, and it gives you an output. Although it's doing well, but we don't know how exactly the model works, and that's the biggest issue in like applying machine learning model in science community. Sorry, not in science, in physics community, that people seeing machine learning model is a black box. If we want to know what's happening inside the machine learning model, we need some interpretable model that we can know what's happening, what's driven the dynamics, so that we can help the physics to develop further. So on the right, I'm showing a figure generated by Midjourney, which is opening the black box of Earth's radiation belt, which is the next part I would like to discuss. The first thing is the machine learning model trustable? So although you can have those very good performance, what you got is just like a similar data set. You cannot say it's physically capture the dynamics there. The second thing is, okay, if our model is trustable, what can we learn from these, right? When you got a model, you're not just like trying to model it, you want to learn something from it. And the third thing is, we already did an amazing job in understanding machine learning, understanding radiation belt physics. How to combine with those known physics that we already know, like during this decades. So that's the next part I would like to speak about. The first part is like how to understand the machine learning model. One thing is we can learn that from game theory. Because if you consider machine learning model, it's got a different input and you somehow got some output flux. It's a nonlinear model. And for nonlinear model, it's very difficult to get the interaction between different parameters and what's the feature contribution there. Fortunately, there are some ways. So here I'm showing an example in game theory there are 3 people, they trying to play games to get, get some profit, get money. So when there is no people, well, definitely it's 0. So when A play alone, it's $7. When B play alone, it's $4. When C play alone, it's $6. But interesting, when you see when A plus B plus C, it's not equal to their total contribution, which is 17, it's not equal to 19. The reason is that when different people cooperate with each other, their combination is different. For example, this A plus C, it's not 15, right? Because they play together, they make better profit. So the question is, once they 3 play the game, they earn $19, how to share? How to share fairly? And this is the idea of Shapley value, which is you use the marginal contribution calculated in every combination. So imagine A play first, then C play, then B play. So you could see that A earned $7, which is A alone, and then B comes in, which is $8. And this comes from the marginal contribution of C, which is this A plus C minus A. So this is 8. And finally, you got B, which is 19 minus this 15. So this is like one combination, A versus C and B. What about like, and we know like there are 6 different combinations, right? So that in this way, we can calculate the average marginal contribution from each combination. And from all the combinations, we can finally calculate the contribution from A and B and C, which I listed here. And importantly, when you add those contributions together, it equals the total profit they earn. Okay, so that's the idea of Shapley value. And it's been proved that this Shapley value is the only fair sharing method for in this kind of game theory problem. And to apply this into machine learning model, it's kind of a similar story, because if you think this problem, it's a nonlinear problem, right? You got A and B and C. You can transfer those players into features when you're considering the machine learning model. But there are some 2 major questions. The first is how to describe missingness. When I say missingness, it's like if you think back in our machine learning model, when you got input, you always, when you set, for example, your input, we say like 120 features. If you are familiar with neural network, it's just the 120 features. You cannot remove one features and saying, oh, right now I want just to use those 119 features. It cannot happen. But in this Shapley value, you can describe the missingness because, well, right now this is C alone, play alone, right? So the missingness is an important thing we need to consider. The second problem is how to handle the NP-hard problem. So the NP-hard problem is that, okay, you got 3 features, you only got 3 players, but you need to consider 6 combinations here. What if you got 100 features, 1,000 features, right? It's very difficult. And I can tell you for us, our machine learning input, we got some 18 days history with 2-hour resolution of the input SolarWind data and the geometric indices. So it's close to, it's almost like 1,000 features. We cannot capture, we cannot calculate all the possible combinations there, right? So how to handle that? So for the interest of time, I might gonna skip this part, but the idea is that when you trying to model the missingness, for example, you got a feature A, feature B, and feature C. How to model this missingness? People in machine learning community, they produce some idea called SHAP, which is using expectation to estimate the missing value. So that, okay, we don't have this feature, but we can use we can grab a lot of samples from our input data set, and we capture a mean background of this feature. so that we can provide a background feature to estimate the missing value here. So that's the idea of kernel SHAP. I'll just skip this. And by the way, this paper is by Landberg and Lee in 2017, and it's very famous, like 10,000 citations there. So if you want to check in the detail, please feel free to contact me or like check their paper. The second problem to solve this is that how to figure out that NP-hard problem is how to estimate Shapley value faster. In their way, it's assume a linear model. So for a linear model, here is an example. You got some input here, you got some output here, and this is like a linear equation. And your fx can be written in this way, omega x plus b there, so that when there is no feature, your expectation is just this b, the EFX there. And the contribution for linear, which is also simple, just this coefficient times the x minus the expectation there, right? So this is simple. And once we assume linear model, we can, if you look at the neural network, it's consists of different structures with different neurons there. In each layer, we can again assume it's a linear, right? So that for an output, Fy here, we can back propagate it with some chain rule there. With linear approximation, we can estimate the contribution very fast. And this is also in their SHAP paper. I'm not gonna talk about the details in their in this SHAP method, but the basic idea is that we successfully changed the players I mentioned previously to the features in our model. So basically, for each feature's contribution, which is the SHAP value, is here. Once you combine all those feature contribution together, the properties of this SHAP value is very similar to the Shapley value, and it equals to your model local output minus the average, which is the background of your data samples. And again, this paper is unified approach to interpreting model predictions by Landberg and Lee in 2017. Please check it. It's very useful. So how to convert this idea into our model? Here I'm showing the framework. So remember, we got some input time history of different geometric indices, for example, AL, CMH, pressure, and solar wind speed there. We input that into a neural network. We got some output at some locations, right? Right now, we back propagate it into this black box. We investigate how to use SHAP explainer here. So for each output, for example, like this T0 electron flux around 3 point, for log scale, like around 3.5 something, you can calculate the contribution of different parameters at different time. So for example, this ALT minus 7 means like happens at 7 hours ahead, 7 hours ahead of this T0. The contribution is positive, marking at right here. And this CMH, meaning this CMH happens at T0, the contribution is minus there. And we can calculate this across all the L shell. And finally, we can color coded it on the input we shown here. So you could again see the CMH contribution here, positive, negative at here. For all the AL cluster, you could see those enhancements very clearly, right? So this is the idea of our SHAP contributions. We can turn the feature contribution, we can map the feature contributions onto our input, and we can see what contribute to the positive thing, what contribute to the negative, what's trying to enhance the flux finally, what's trying to reduce the flux there. So let me show one example in storm time result. So this is a storm time. Again, this is the the trajectory is the measurement, and the last panel is the reconstruction of the machine learning model. So the first machine learning model captures the right dynamics there. At time A, we calculate the SHAP value. So you could see it's very close to, the white color means it's very close to 0, right? There is no positive contribution, there is no negative contribution, and it's reasonable because there's no dynamics happening there. But when we look at time B, when the dropout happens, you could see there is a decrease in image, and there is a decrease because of this pressure enhancement. And interestingly, you could see the contribution from AL is positive, right? Although those things happen together in your model, our SHAP method could separate them reasonably. And the most important thing is, for time B, for example, like this, we see the pressure enhancement contribute negatively, and it contributes negatively only at L larger than 4, which is consistent with magnetopause shadowing effect. So that when you got an enhancement in dynamic pressure, you're compress the magnetopause, and the electron drift outwards of the magnetopause and become radial diffusion to higher L shell. Sorry. So that's the magnetopause shadowing effect. It's very close to our physics understanding. And when you look at time C, the electron flux start to get enhanced. You could see the enhancement for all the L shell basically come from those AL enhancement. And the main phase of image contributes to the dropout at higher L shell, but enhancement at lower L shell. It's possibly due to the DST effect because the conversation of adiabatic environment. And you could see that here at time D, again, those enhancement is very clear in this AL cluster here, and the DST minimum for lower L shell, right? So for storm time, we are kind of familiar. We know that the AL cluster is very close, very related to the substorm activity. But what about non-storm time, which we don't know very well? With this method, we can identify what's happening in the radiation belt and where we should focus. So for example, this is non-storm time. At time A, there is again, there is no much dynamics, but at time B and C and D, when there is enhancement, you could clearly see those AL contribute to the enhancement of the electron flux, and the strongest peak coincide with the highest feature contribution here, right? Again, this tells us this non-storm enhancement might due to an injection, and this can help us locate where to find the physical process. And this further demonstrates our machine learning model is deliverable because it's consistent with our physical understanding. And another very important thing is it can quantify the contribution for different driver, because in radiation belt, a lot of things happen together, right? You got a solar wind enhancement, you got an IMF BZ profile, so you got more reconnection, you got a more stronger storm time, you got more stronger substorm activities, and also you got usually during those time you got a big storm there. So those things always happen together. But right with this method, we can quantify what's the contribution for different drivers. And that leads us to another study, which we want to invest with this model. We want to, again, trying to reinvestigate a lot of questions we already discussed during those decades that people have discussed before with new methods to see what we can see. So for example, this is an acceleration and depletion event, very famous by Reeves in 2003, which is that when the electron flux, when there is a storm, the electron flux, sometimes you got enhancement, sometimes you got drop off. And for example, in this one, you got the enhancement here, but for this one, you got dropout here. We got depletion here, and for this one is like basically non-change. Their conclusion is that it's because of the high solar wind speed, but that might not be true. So what we did is that we reinvestigate this with our SHAP method we mentioned. So in this case, you got a depletion. Again, our model successfully captured this depletion here. You can see at time at beginning of time, like there nothing happened, but for the afterwards, those period, you could see the depletion directly comes from the enhancement of dynamic pressure. And also the important part is that it comes from this quiet time AL index. So you could see the quiet time AL after this CMH minimum, after the main phase of the storm or the pressure enhancement, the contribution is negative, right? Although there is a very strong injection here, the contribution afterwards is negative. And I can tell you because our feature contribution is addable. So you can add those negative contribution, and it's very those contribution is huge. So it tells us the pressure and quiet time AL index can contribute to the depletion. But in statistically, how we can study this accurately. And if we compare the acceleration, we can see this comes from the balance between acceleration and loss. For this acceleration process, you got a very strong AL cluster, so that basically it contributes to the enhancement. But for this depletion, although you got some contribution previously for the injection there, after this pressure maximum, those quiet time AL, the negative contribution kind of leads to the depletion, flux depletion there. And this leads us to trying to do this in statistical way to try to investigate whether it's because of the continuous high intensity substorm or it's because of some storm substorm relation, like what's happening there. So people already did this previously, like they use a superposed epoch analysis to study this. But the one thing I would like to show is that with this SHAP method, what we can do. So we use, for example, like 20 or 30 events, we put those things together. The T0 is the pressure maximum, which is very familiar, superposed epoch analysis. And you could see the quantile here, the upper quantile and the lower quantile. And it tells you, oh, it might be because of the storm, it might be because of the enhancement there. But one thing is, with this SHAP method, we can statistically calculate all the SHAP contributions for all the events. And you could immediately see that when the dropout happens, the contribution comes from the CMH minimum and the pressure enhancement, which leads us to the magnetopause shadowing effect. And for the later part acceleration, you could see the AL cluster dominate this process. And for 2 days after the pressure maximum, you could still see this enhancement is due to the AL cluster. And we can compare it with depletion. So that's exactly the way people did previously with superposed epoch analysis. We just put the SHAP method on that. But importantly, you could see for depletion, again, you also got a dropout period when you calculate the flux at T0 plus 5. So like 5 hours, there is a dropout happens. It's because of the pressure maximum. But importantly, when you look at 2 days after this depletion, you can see all the negative contribution is from this quiet AL. And this is not just from one event, it's come from all the events we studied, we used in this superposed epoch analysis. So this tells us the story, which is the enhancement is there. But for the depletion, it might just be a non-enhanced event because the substorm after the pressure maximum is just not strong enough to accelerate the flux back to its previous value. Because in both events, in both enhancement and depletion events, you always experience this pressure maximum, this dropout there, right? So we use statistical result directly from satellites. Again, this time is not from machine learning model results. So for A, here I'm showing the integral AL or the average AL after the pressure maximum, so that you could see for this flux is the initial value for reference. The blue one is the flux at dropout stage, which is 5 hours indicated by our superposed epoch analysis. The right one is 2 days after the pressure maximum. So you could see for very low AL, average AL after the pressure maximum, the flux is not enhanced to the previous value. But for like a stronger substorm activity, this can be enhanced here, larger than the initial value. And for very strong substorm activity, it's enhanced like very clearly here. And this one shows a very good linear correlation between the average AL and the flux at T plus 2 days. And again, this result is not like from experience, it's just directly from our data-driven method, and it's seen in the SHAP method. Another thing is, when previously people are talking about this is due to the high speed solar wind, but it's not very true, because if you compare this flux with solar wind, there is no very good correlation there, and the correlation between the average AL and solar wind is also like not a very good linear correlation. The reason is that the AL actually, what we're seeing here, let me show this. Yeah. So what we're seeing here, although those two events, they both have high solar wind speed, but their IMF BZ profile is different. The duration of the BZ is different, so that it leads to different substorm activity after the pressure maximum. And this high solar wind speed effect is already captured in this AL thing. So we didn't consider the what's happening in the solar wind speed. We just look at the AL there. So let me see if I got any other slides. Yep. So here is the takeaway. We built a set of machine learning models that could well capture electron dynamics in radiation belts from 50 keV to 2 MeV. For high energy, we still like very high energy, we are still working on it. And again, we use some interpretable machine learning method, which is called SHAP. It gave us feature importance result that is same with our physical understanding. And we further utilize this method to investigate depletion and enhancement results, which shows that the pressure drives the loss process, and the duration of the ensuing substorm sequence, that's the the key feature that determine whether the electron fluxes result in enhancement or depletion. So I'll stop here and welcome to any question. Thank you.
All right, thank you, Donglai, for a really, really cool talk. We have a couple questions coming in, so I'll ask them first, and then I have a couple of myself as well. So Elizaveta asks, what do you think about taking into account the adiabatic effect in the changes of relativistic electrons? Is that something you might be able to do in the machine learning or in a machine learning model?
This is a very, very good question. So for adiabatic effect, let's see what the first thing is, what we see from model, right? What we see from model, and a very important thing we say here is that for CMH, usually like the CMH close to the T0, close to the flux we measure, is the feature that we are not very, how's that? We are not very not from we fail to understand very reasonably like for those things, because sometimes it gives you negative value, sometimes it gives you positive value like at the beginning. It's for this thing we are still under investigate. But the answer to your question is that I think we need to model the phase space density directly instead of the electron flux. So the reason we start with electron flux is, first, we got good data coverage for this. We don't need pitch angle distribution. This is like integral flux, right? The phase space density, I'm telling you, like we are working on that in our group, and we know other group, they are working on the like modeling the phase space density directly. I think if we can model that, the adiabatic effect, like we might can capture it, right? Mm-hmm. That's the important thing. And another thing is the driver, we actually include the position there. So it might be like a model the different L shell together. For example, right now we only got one output at one location. So in the future, we can get 10 output at different L shell with phase space density. Then we can say what's the adiabatic effect in the changes in electrons there. So I hope this kind of answers the questions.
Mm-hmm. Yeah, excellent. So I had a question with regard to the SHAP values. Mm-hmm. You use a linear approximation or linear model. So does that mean for the SHAP values, you have to calculate that linear model for every possible combination of variables in your neural network?
Yeah, that's the thing we skipped. So the good part is, if you consider linear model, once this is a linear model, you can, and you use the chain rule and the linear approximation. The important part is this function here. If once you got this linear approximation, when you got a linear model, when you got a neural network model there, you calculate, let's see, forward, right? You got the output. And when you backward there, you can just based on the linear approximation to directly get the SHAP value for each feature. You don't need you don't need the combination for different features. And that's the important part of a linear assumption there, right? So for kernel SHAP, which I shown here, this is not a linear assumption. This is just, let's say, using expectation to calculate this. It still needs to calculate different correlations there if you look at the way to calculate the coefficients there. But with neural network, it's very, very hard to directly use the kernel SHAP method, which we don't need a linear approximation. But here, like, let's see, with linear approximation, you can directly calculate it. It's like embedded in your neural network backward, very fast. You can calculate it.
Okay, excellent, cool. So that's all the questions we have for today. So I'd like to thank you again for a really cool talk.
I think there is another question. Is that Sasha?
No, it's a thank you for an interesting talk. Yeah.
Thank you so much.
Yeah. So next week we'll have not a similar talk, but we'll be continuing some of the machine learning talks that we've had in the last little bit. And Michael Coughlin will be discussing ground magnetic perturbation predictions using machine learning and interpretability methods. So we'll be building on what Lei presented today, but looking at magnetic perturbations on the ground.
Sorry to interrupt, but Sasha did have a question. He said.
Oh, I thought he was clapping. Sorry, Sasha. Yeah. I thought you were clapping. Go ahead.
Yeah, thank you very much. Yes, so those symbols are very similar. Yeah, this is the very excellent overview of what machine learning can do. And I hope my questions will be short, so I don't want to delay everyone. So when you do the split of the data and the validation and discuss the problem of the data leakage, so you end up using some chunks of 2 to 30 days, and is there a methodology that you use to select those periods of time, and what's the distribution of the gammatic activity for the validation periods? And the second question, maybe you can just answer both of them. your reconstruction works pretty much for Van Allen probes, but how well the machine learning, or is there anything that you have to do to change in order to train the modeling, your model to construct the flux at the LEO satellite, for the LEO satellites, or for Arasi? So like basically on a different orbits, how would that work? Thanks.
Okay, Sarah, thank you so much for all the questions. I really appreciate those questions. So for the first question, let's see. Do I need to share the screen again? I'll just say that. So for 2 to 30 days selection, as I said, the only criteria I came up is that it need to be much higher than the resolution of your data samples, which is 5 minutes, and much lower than your 5 years data samples. And that's from purely view of machine learning method that we want to keep the distribution like in training and test data reasonable, and also like there is no data leakage. But how to select this, how to do this very rigorously, and it's very hard, because when you change you need to do a lot of experiment to see like what's the performance on your data set. So we just like say, oh, it's a okay performance, so that we stop there. We don't have very rigorous discussion there. For 2 days to 30 days is that when we first build this model, we want to consider that because the sun got 27 days period, right? We want to say, we want to see whether this 30 days can capture, can do some better job. But it turns out like you lower than this 27 period, it's okay there. So yeah, I remember after your first question, you at the end of your first question, you said something else. I think I didn't capture, but I'll.
It was a question about distribution of geomagnetic activity. So basically, when you select the validation period, do you have the same distribution of KP or AL as for the training?
I don't have that, and that's that's actually unexpected result from our side. So it's working. So that's one important thing. So for second question, could you repeat your second question again?
Yeah, basically, can you use machine learning that you built for Leo and Arasi?
For LEO. Again, from purely a machine learning view, like when you don't have LEO data in your model, so you cannot model LEO data. That's the simple answer. In the future, we want to include those different observations. For example, LEO or those things. We actually start to look at post data, like the combination. What we can do, whether we can use equatorial flux to reconstruct LEO or use LEO to reconstruct equatorial, because LEO is much cheaper, right? So yeah, we are considering that. But with this model only, I don't think we can model the LEO orbit, although we can estimate that because we got some latitude distribution, but it's not, the coverage is not there. So we can't. That's the reasonable answer, because the model did not train on those orbits. Thank you.
All right, excellent. Thank you for the question, Sasha, and sorry again for missing that. Again, so Mike will be talking next week, following on from Donglai's talk, talking about ground-based magnetometer perturbations. So I hope to see everyone next week, and thank you again, Donglai.
Thank you all. Bye.
Bye.